Now it's time to cover array operations and join techniques. Array workloads are rich and depend on the application domain. So ArrayDBMSs provide a set of core operations and allow users to code sophisticated array processing using UDFs. Researchers also optimize popular complex operations and introduce novel operators. Let's cover them in more detail. First, let me remind you the multidimensional array data model that we use in this tutorial. Please recall that an array shape is a tuple with the length of array axis. In addition, a hyperslab of an array is its subarray. Hyperslabbing is an extraction of a hyperslab from an array. Hyperslabbing is one of the core operations that is present in all array DBMSs. Reshaping changes the order of array axes given a permutation. For a 2D case, reshaping is reduced to the matrix transposition. As a consequence, reshaping alters the array storage layout according to the given order of dimensions. Hence, reshaping helps to achieve the fastest hyperslabbing along a dimension. For example, reading a time series. This is an additional practical use case for reshaping. Downsampling creates a coarser version of an array. Popular map services build multi-resolution pyramids using downsampling. Interpolation is a core operation with many applications. It estimates an unknown value between the known coordinates. How complex is resampling? Well, a schoolboy can perform nearest neighbor resampling for a tiny matrix on a piece of paper. However, arrays can be georeferenced, they are large, and we process them in a distributed fashion. So, if everything is ready, like metadata management, core operations, and even resampling code for one cluster node, only the preparation for resampling takes about 1,000 lines of code. A generic aggregation produces an array with a dimensionality less than the input array. Examples include monthly mean temperature, zonal or global averages. Structural aggregations process hyperslabs. They divide a hyperslab into multiple and possibly overlapping arrays and then return multiple aggregation results at a time. Structural aggregations can also be combined with value-based filtering conditions. To increase the signal-to-noise ratio, coaddition takes a time series of astronomical observations, a 3D array, for the same area and sums up pixel values. Before summing up the pixel values, it performs iterative outlier removal. Array algebra is an analysis language that is widely used in the industry. It defines a rich set of operations categorized into the following types: local, cell-wise; focal, neighborhood-wise; zonal, region-wise, where regions are defined by a function; and global. For example, local operations include arithmetic operations, masking, if-then-else expression, Boolean, and relational expressions. We already covered the IndieGuy example, which takes two two-dimensional arrays as input and produces a two-dimensional array as output. Recently, top-K queries for ArrayDBMSs were first introduced. Users provide a scoring function, for example, a median of cell values, a selection condition, that is a kind of a filtering criterion, like the average of cell values should not exceed some threshold, and a fixed shape. The output can be computed progressively and contains fixed-size hyperslabs that have the provided shape. These hyperslabs should satisfy this selection condition. They are sorted using the scoring function, and only the top k hyperslabs are returned. Difference histograms provide a big picture of the differences between arrays. As an example, consider arrays T1 and T2. The intensity of gray color reflects the value magnitude. To grasp the high-level differences between these two arrays, a difference histogram is built using a quad tree. It has varying cell sizes. The colors reflect the magnitude of differences. For example, hot colors indicate a larger increase of values from T1 to T2. This technique can be used to compare simulation or observation datasets. Array joins substantially differ from relational table joins. Like relational joins, the array join is always a hot research topic. In addition, there is a wide variety of array join types, and array join is one of the most complex operations. Likewise, a relational join. When arrays can store a tuple of values in a single cell, array attribute join is possible. As a result, you get an array of the same dimensionality with a tuple of attributes joined from input arrays. As input, the k-way array join takes k arrays and several functions. Input arrays may have different shapes. As a result, you get an array that covers all input arrays. That is, a hyperslab exists that can produce any axis of any input array from an axis of an output array. Cells of the output array are computed by a user-defined function. So this user-defined function takes as input the values of spatially collocated cells of all input arrays. Inner and outer join types differ in a way how no data values are treated. We will cover in depth this join technique during the in situ techniques part of this tutorial. Here we have two two-dimensional arrays, alpha and beta, as inputs. Equijoin returns the cells with the same coordinates that are equal in both input arrays. Value similarity join returns the cell pairs also with the same coordinates, but with value difference less or equal than a threshold. Dimension similarity join returns the matching cell pairs with difference between their coordinates not greater than a threshold. Array similarity join with a shape array generalizes the previous similarity joins. As input, it takes a shape, a comparison function, for example, an identity, and two multidimensional arrays. On the slide, the shape array is a one-dimensional array with two cells. We seek a cell with index j from alpha, which is similar equals in this case, with any cell within the shape from beta. For example, alpha ij equals beta ij, or alpha ij equals beta ij plus 1 according to the shape array. For example, the green cell in tau, that is the resulting array, with index 323, indicates that alpha 32 equals beta 2 plus 1. The resulting array dimensionality is larger than the dimensionality of any input array. This is done to be able to reconstruct the positions of cells of any input array that contributed to the result. For example, with index 323, we can easily derive indices 3, 2 of alpha and 3 of beta. How to efficiently recompute array similarity joins. For two arrays, a materialized view is their similarity join. Updates to these arrays, namely delta and alpha, come in batches at fixed time steps. The task is to maintain the materialized view, and the core idea is to do this indirectly. First, compute a differential view and then merge it with the existing view. The solution consists of three parts. First, create an optimized plan to compute the differential view delta V. After that, identify nodes to compute the merging. Finally, reassign view chunks between cluster nodes. In this way, it's possible to reduce the computation and communication cost of array view maintenance. Array UDF runs UDFs on multidimensional windows of an input array. One of its core contributions is the possibility to automatically select chunk shapes. The first heuristic chooses a chunk shape as the largest ND subarray that fits into the RAM of a process. In this case, all axes have equal lengths. In the 3D case, it's a cube. The second heuristic also respects memory limitations, but it selects the shape to be proportional to the sizes of axes of the input array. UDFs are used to code sophisticated array processing. For example, researchers evaluated SciDB on neuroscience and astronomy pipelines. They used UDFs in Python to code some steps. However, UDFs in Python or C++ or other similar language are black boxes to array DBMSs that cannot be optimized. CHRONOSDB provides the first native UDF language for array DBMSs. A part of the UDF you see on this slide encodes the logic for road traffic simulation. The UDF looks small, but is challenging to execute. For instance, the same array name appears several times. The lastCal command deletes the current speed array and creates a new array with the same name. Unlike Python and C++ UDFs, CHRONOSDB native UDFs are optimized by compiler techniques and strict formal definitions of array operations. We will have a look at one of the simulation results in just a few minutes. Now, let me present a novel research and development direction in the area of array DBMS. It opens a large variety of promising and exciting research and development opportunities. Array DBMSs manage big multidimensional array storage, processing, and even visualization in some cases. Physical world simulations have been traditionally implemented on diverse types of grids and meshes that can be modeled as ND arrays. As multidimensional arrays are at the core of array DBMS, it is logical to apply array DBMSs to physical simulations to benefit from array DBMS capabilities. Cellular Automata seem to be a good starting point for integrating simulations into array DBMSs due to having multidimensional array models for their lattices and numerous successful applications. We solved multiple design challenges to enable cellular automata simulations possible inside array DBMS. They are related to iterative workloads, cellular automata transition rules, parallel execution, and other challenges. A database approach to physical simulation brings numerous benefits. Let us take CHRONOSDB as an example. It enables automatic parallelization, easy debugging, DBMS-like data management, and interactive visualization, to name a few. Currently, only CHRONOSDB supports both end-to-end Cellular Automata simulations and DBMS data-like simulation data management. If you perform simulations, you will always need to manage your input data, output data, share and visualize your results. In general, you're more productive if you can use only one system to accomplish all your goals quickly and easily without data migration. As an example, we constructed a complex road traffic cellular automaton based on the literature with multiple lanes, road intersections, traffic lights, different vehicles' speed, different vehicles' lengths, varying and complex vehicle behavior. We took a traditional cellular automaton grid that is used in state-of-the-art research, an artificial road map resembling the Manhattan Grid, New York City. Let us showcase one of the benefits of running the simulations inside ArrayDBMS. CHRONOSDB provides array imagery via an open, popular web mapping protocol. Hence, users can watch the modeling at work on an interactive web map. How vehicles move along the roads, queue at traffic lights, turn at road crossings, accelerate, brake, change lanes, and overtake each other. To our best knowledge, our work is the first to run end-to-end cellular automata simulations completely inside ArrayDBMS. We enable ArrayDBMS to simulate the physical world for the first time. Please learn more about this exciting novel direction at the paper homepage you see at the bottom left. Let me briefly mention the most promising R&D opportunities for this part of the tutorial. For ArrayDBMSs, novel applications are the major drivers for innovations. Diverse scientific communities collected and processed array data for decades before ArrayDBMSs appeared. If we would like to add value, we immediately discover many unexplored ArrayDBMS applications that are a fruitful ground for new data management challenges.